That's why I always type it
Okay,
up.
I'm Donovan Wixom. I'm doing problem 4, and hopefully I'm doing it right this time. So, part A says to determine the allele frequency of R2 and R3. So to find the allele frequency, we'll start with R2 first. We know that the genotype frequency, we know that the homozygous R2 appear 135 times. So to find p squared, or the genotype frequency, we just do 135 divided by our total population, 190, which gives us this beautiful number. And then we do the same thing for our 3 homozygous. We know they showed up 11 times. So q squared is 11 divided by 190, which gives us this beautiful number. So to find the frequencies, the allele frequencies are equal to p and q. And since we found p squared and q squared, we just have to take the square roots of these two numbers. So the allele frequency for this one's R2, we just take the square root of that. We get 0.842927. And for R3, take the square root of this, which is 0.240613. That is our allele frequencies. For part B, we're going to need them to find our expected. So let's think about this for a second. Sorry. So our expected for R2, we know, holy cow, I just lost my train of thought. Square it, right. We know this. It's p squared. We just found p. We found p using p squared. So you can either just re-square this, or you can just take that number, 0.710526. That's a 0. And then you multiply it by our total population. So you're going to get basically the same number that our population was. I got like 134.99, a lot of nines, basically. That's going to be the same, basically the same thing for the homozygous R3s. That's equal to q squared. Again, you can square this or just steal that number from up here, 0.05789 times 190. Our expected population, I got like 10.9 repeating. So basically, I'm doing all this math. So the real question is, how close is our expected heterozygous? To get our heterozygous expected, that is equal to 2pq. Well, our p and q are right up here. So 2 times 0.842927 times 0.240613 gives us 0.40563839. Times that by our total population, we get an expected of 77.071293, yada yada yada. So that is pretty different from our actual observed 44, but we're going to do a chi-square just to see if it is actually correct. So yeah, set up your chi-squared. Our observed for, I'm starting with this one, minus our expected, 0.9 repeating, plus our observed, well now we'll do the homozygous R3. Our observed was 11 minus like 10.9 repeating over 10.9. And now we'll do our heterozygous. We had 44 minus our 77.071293 over 77.071293. Okay, so for these two, since they're so close, when I did the math, they're basically 0. This one was about 2.6 repeating times 10 to the negative 11th. And just because of the number I used for this one, I got another really small number. It was like 0. It was like 9 times 10 to like negative 9th. They were both really small. This one, when I did it, I got about 14.190892. And since those are so small, I did bother to add them in my calculator, and it like literally didn't change this. That's our chi-squared. If you look at the table, that is, am I doing it wrong? Your face looks like I'm doing it wrong. Okay. That's the chi-squared I got. When you look at the table, that means we reject the null hypothesis, which means that this population is not in equilibrium. There is some sort of evolution occurring.
You know what? I have faith.